Okay. So for example, you can do something like this, right? You can say plot the PDF, plot the CDF. You can ask the probability and all kind of thing, right? Okay. So something like this, right? So this would be, and let's say that you have a data set and this is what you come up with, then you can ask all kind of stuff, interrogate what the value is and you know, say what value of X between A and B is, so forth. Okay, that sort of thing. So maybe you should something like this. Probability of this. Yeah, something like that. Let's see. Okay, Cap. So welcome back to the second half. Before the break, I show you what you'd be expected to do, you know, say on the midterm, combine your understanding of how to play with probability function and just, you know, mix it with interactive visualization. So for example, this seems like a reasonable thing to ask for you to produce during the exam. Okay, I'm not going to ask you exactly this, but and each one of you be different. So let's say you are assigned to say, oh, show something about binomial distribution. Well, what can you do with binomial distribution? You can certainly show the PDF and CDF, right? And then you can play around with different N, right? And different P, right? And based on that assumption, you can calculate this. You can say, you know, what's the probability X between A and B, given that X has binomial distribution N and P, right? And then allow this to be N and P, would A and B would be your interrogator. Okay. So conceptually, N and P would be coming from your data, right? The data is what dictates what N and P would look like because that's the parameter of the distribution. But once you got that insight, the user wants to know something, right? User wants to know something, then he can interrogate, okay, what's the probability between A and B? And I set different value for A, different value for B, okay? In this case, probability X between 0.95 and 3 is equal to 0.57. Okay. Notice that A and B can be continuous, but it doesn't matter because the probability only happens at the discrete point, right? Okay. So this here, and let me highlight. Let me add this thing called delimiter. Just so it's sort of a nice line, right? So something like okay, let's write this is called distributional parameter. Okay. So we write that and then delimiter, and then this will be something like inquiry endpoint or something. Okay. Something like that, right? Okay. So may I just make it style? This is a little bit like HTML, but not quite. So something like bold. Okay. Yeah, it's a bit bigger. Okay. And RGB color. Let's red, green, blue, 0, 0, 1. Oops, does that work? All right. Yeah. What is it? RGB color. Right. Okay, so let's do that. So this would be an example of, quote unquote, that again, you guys are Basai people, so you should think in terms of design as well. So it's not, think of user interface or something. Like oops, what happened? Right, okay. Something like that. I don't know. Right. So play around with this, okay? It's completely reasonable for me to ask you to do this sort of thing. In a space of 5 minutes or so. I can send you this, just an example, okay? Right. So what does this do? This is manipulate, right? This set up the interactivity, right? These are the things that you play with. N is the parameter, the distribution. So it's P, inquiry endpoint, okay? So inquiry parameter is A and B, right? And what do you have here? I have grid function. Now grid is going to have basically it's kind of like arranging things in grid, obviously, right? So the first line would has two things. There's a discrete plot of a PDF, and there's a continuous plot of a CDF. And the second line has this text. This is a text join. This convert the number into string. So probability open bracket of A less than equal to X less than equal to B equal to, and then this is the calculation, right? Something like that. So there, that's it. That's your thing. That's your tool. Okay. Now, the example I was giving you would be something like, instead of having this, it would be, well, I make it a little bit even nicer. Never mind. Just say something like you build a model in here, and that is a regression. So instead of having a distribution, a binomial distribution, it would be a distribution of something as a regression of equation of something else or something like that. So all kind of stuff you can play with, right? But again, this supposedly came from data. Now, so let's go to what inferential statistic looks like. So, by the way, you should read what's called central limit theorem. It's very, very nice piece of mathematics. Actually, it's in Wikipedia, right? What does it say? Well, you can say it in Word, right? It doesn't matter what the original population distribution is. If you take a large sample of it at the time, say 30, usually 30 is like a magic word, okay? Once you get a sample of 30 or more, the distribution of that will look like a normal. That's why this 30 is sort of like a magic number that in most studies you say, oh, we can't get that many sample, but we try to get as many as 30 at the minimum or something. That 30 comes from this. What happened is, if you don't get 30, you would get to a shape called student's T. And that's another one, okay? But once you get to 30, then you get to this nice normal shape. Okay, right. So let's go to inferential statistic. So this is probability model. Let's go to different. Okay. Now, I'm not going to cover Bayesian in this class, right? But the way you think about it is like you think of all kind of conditional, okay? And you might pick up a little bit of Bayesian insight when you go to machine learning, because there's actually a technique there called Bayesian decision tree or naive Bayesian tree or something like that. But basically, we're going to do classical. Again, what's the classical? Classical assume that we're working with frequency. Okay. The way I see it, there are actually 4 kind of questions you play with. Okay, we already talked about two of them. One is distribution fit. That's like, this is a data set. What is the best function you can fit on it? Okay. And you can choose from a 300 or you can choose from 10. Okay. But whatever you chose, you still have to estimate the parameter. Okay. So you try to do all kind of detailed analysis on just that one distribution, that one population. Okay. Based on the data. Second, hypothesis testing. This is when you ask a lot of questions. And for here, most of the question will be about the means of different population. So this hypothesis testing will tend to be a bit like that, asking about the means. Or the other thing I can ask is a combination of the beginning. If you came up with the distribution, okay, let's say you fit this data, and for some reason, okay, your best fit is this data has gamma distribution with parameter 2 and 3. You don't care what that is, okay? Hypothesis testing would be something like, what if you didn't do this yourself? Somebody just told you that the data follow gamma 2, 3. Okay? Hypothesis is, yes, this guy is telling you the truth. Now, that's the null hypothesis. Alternative hypothesis is, nah, this guy is nonsense. Okay? So instead of asking whether or not the means are equal, you can ask whether or not the data support the claim. So that's why it's called, general term is called, it's not called comparing the means, it's called hypothesis testing. Because there has to be a hypothesis that somebody claims. Okay? And the data would say, I reject it or not. A good example, for example, a good example would be this. You run sustainability or environmental campaign, and you want to make sure that the water quality has this no more than this level of hard metal. Okay, so maybe cadmium is a bad thing for the environment. Okay, so there's a concentration of cadmium that's bad for the health. And you just take sample from the water runoff from this factory, right? So obviously the claim would be like this. The factory would claim, okay, because the limit of cadmium is 2.7 part per billion. I don't know, okay? Just say 2.7 part per billion, okay? So the claim would be that the average cadmium concentration coming from this factory is 2.4 part per billion. Alternatively, is higher. So you reject. Okay? If you reject with enough confidence, probabilistic confidence, you can take the factory to court. Okay? What it means is this, in terms of statistical evidence in court, when you say the hard limit is 2.4 and the mean is actually no higher than 2.4, is it possible that for the 10 days that you sample the water, you get 2.5? Yes, it is possible, right? Right? So if the true means is, let's say the true mean is not even 2.4, true mean is 2.3. So this is really a good factory. Is it possible that you would actually sample water for 10 days and get a reading of 2.5? It's possible. It's possible. Now, if the mean is 2.3 and you take sample for 10 days, it's, yeah, maybe you can get 2.5. The court is not going to convict the company. But if you collect the sample for 1,000 days and still the average is 2.5, then you're starting to say, oh, this is not believable. Conversely, you collect for 10 days as before, but the number that you came up with is 5.7. It's really way out there. Okay? So the number of data you take makes the evaluation threshold more precise, your test statistic more precise. But it's also how far away from the claim. The claim is 2.4. If it's 5.7, chances are this guy really exceeds the limit. Okay. And there is a probability associated with that. So in other words, if you collect data for 10 days, okay, the claim is 2.4. There's a probability that you would observe number of 2.5 or higher. That is called a p-value. If that p-value is high, you give the factory the benefit of a doubt. But if the value is like 5.7, the p-value is going to be tiny. You know, that your true mean is 2.4, but from this 10-day, I get some number as 5.7. The probability of getting some number that big or worse is 0.00001. If you came up with this is an extremely low p-value. The court can convict you. Okay. Now it depends on certain things. If it's environmental court, maybe p-value of 0.01 would be considered a threshold. Anything below that, yes, you have to find the company. Right? If it's something more, I don't know, international border or something with, you know, a bigger implication politically, maybe you would have p of 0.00001 as a cutoff. Okay. But at some point, the p-value matters. Okay. So that would be the sort of thing called hypothesis testing. I'll go into details of how, what sort of question you can do and how easily you can do it with Mathematica. The goodness of fit test would be kind of like what I talk about, which is instead of just testing the mean, you are doing hypothesis testing, but testing against some kind of claim, right? So when you fit the distribution, so right now, just now it's just the mean, but instead if it's just the mean, it's a claim on the distribution. I claim that it is gamma 2,3. I don't believe you, or I believe you. Okay, so that's kind of like goodness of fit test. Finally, there is regression analysis. Regression analysis, in a way, is a form of distribution fit, except instead of fitting one distribution, you fit distribution as a function of factor, right? So it's like a mean PD PM 2.5 as a function of humidity, temperature, all kind of stuff. Okay, so these are basically the four kind of thing you can ask. Again, what does the data look like? How's it distributed? 2, test some kind of hypothesis, like certain claim about the value of a mean, or you can even test on the value of the variance, but most of the time it's the means. You can say, is the mean of this population or the mean of this water higher than 2.4? Okay, or you don't have to compare against a real number. You can compare against competitor. Is this factory releasing more cadmium than the other factory? In which case, it's not versus 2.4. It is mean of this factory minus mean of this factory versus 0. Right? You can do that. You can do that. You can ask all kinds of questions. Right? And this depends on, and this is where real professional analysts comes. They know what kind of tools in that toolkit. Okay, and then you can ask certain questions. You can claim goodness of fit test is a more general case of fitting the whole shape. So hypothesis goodness of fit test is like hypothesis testing on the distribution claim. Okay, and then regression analysis. Okay, so you understand that these are the sort of questions that you'll be asking. All right. When you get to machine learning, same thing. You will learn different technique, but I suggest that you sit back and say, hey, this technique, okay, let's say you learn gradient boosting, okay, it's a technique you use, fine, you came up with the result. Don't just learn how to do it and interpret the result. Think back to yourself, what is the question that it answers? Okay, this is very important. And this is the skill that I emphasize. I mean, you guys are not going to be better statistician than people who study statistics. I don't expect you to, but I expect you to have perspective at all times about what you're doing. Professional statistician, they are so deep into the problem, they don't have to question what they're doing. And in fact, for this kind of problem that they deal with, they don't even have to question. They just use this method, but they just have to do a better job day by day. You guys are different. You're Basai. You are in the job of shopping. You're shopping for different class of probability distribution. You're shopping for different statistical toolkit for different kind of questions. You see what I mean? So you always have to sit back and say, what does this answer? What does ANOVA? ANOVA is a very popular thing, you know, and most statisticians can do it in their dream, right? I don't expect you to do that in your sleep, but I expect you to say, what question does that answer? When will I need it? Because as a Basai student, you will come across different environment, different problem setting that will require you to be very agile. Say, oh, for this thing, I'm going to use this version of ANOVA. For this, I'm going to use, you see what I mean? Okay, so that's very important. So this kind of self-reflection is emphasis. I put a lot more. Right. So let's go to distribution fit. Now, distribution fit, okay, you can think of it as general search. Hey, this is a data set. I don't even know which one. Okay. My teacher gave me a hint that in life, chances are it's one of these 10. But which one? Okay. So it's a very general search. Okay. And there's parametric estimation. Parametric estimation is like, I've decided that it's either going to be student T or logistic based on certain criteria. What are the parameters? Okay, so you choose the function, now get the parameter. Now, of course, this is layered, right? So in reality, the general search, you would try many functions. For each function or each family or each, sometimes they use the word family, they don't use the word name, but I would just say brand, okay? For different brand of probability distribution, estimate the parameter the best you can, and then let them compete. And the one that wins is the overall winner, right? So maybe for this data set, it turns out that gamma with this value of alpha and beta is the best. But if you tried using log normal distribution, you would use this mu and this sigma. That's the best you can do with log normal. Well, now that they are together, let's have them fight off, right? Who's going to be the best? And the overall winner turns out to be log normal or something like that. Okay. Now, in life, it's not that simple. I'll tell you this. In my professional life, a lot of times I have to weigh in what's called, it doesn't happen much in statistics, but in machine learning, but I might as well tell you now. You have to weigh the complexity of the model as well. So sometimes if I have two models and one is clearly more accurate, I told the other one away. But if they are sort of like inconclusive, some data period, this one is better, sometimes this one is a little bit better, okay? However, this one is very simple to explain, like a decision tree, okay? And you can sort of like drill down to find the reasoning and all that. And the other one's a deep neural network, okay? I would recommend to my client to use decision tree. Okay, so the power of the accuracy comes first. Accuracy beats everything, right? Realism. But for similar level of realism, modeling transparency or logic sometimes is a very good thing to consider. Okay, I'm not going to mention anymore, but that's the art. That comes with years of whatever. Right. Okay. So let's go to, okay. By the way, you can go home and play with this. This is all kind of, yeah, the 10 one that I have, binomial distribution, this is all in here, right? So you can shift, and this is sort of like what you saw just now. And okay. Right. So these are all kind of stuff. These are Bernoulli, binomial Bernoulli. Okay, we saw that. We saw a whole bunch of that. That's kind of interesting. Okay, this is sort of what we did before. Okay, it's kind of okay. So this is a fancier version of what I did, where you can actually have a nice looking, pretty. Some of this is cosmetic, you know, like certainly when you have it like this, it looks nicer. Okay, Poisson, it's another one. Okay, I don't have time to go into that, but Poisson is very important. It's like the number of things that accumulates without upper limit, but it's one of those things where you don't expect a lot. So what are kind of rare events that can add up? Well, if you take a car insurance, right? How often do you crash your car? It's not very often, right? So when they write you a car insurance, the number of accidents per year is probably Poisson. Okay, you can have 0 accident, 1 accident, 2 accident. It has no upper limit. Okay, but chances are no human being is going to have more than 20 accidents per year. You have to really be like, you know, on the devil's hit list or something. Okay, but most of the time you probably get around, you know, maybe 2 scratch fender bender kind of thing, right? But it has no upper limit. That's why it goes countably infinite. Poisson is one of those. Okay. The flip side of Poisson is time between accident. That's called exponential. We'll talk about that. That exponential is part of gamma. So this is, so again, I separate this by support, right? By sample set. It's either finite, right? Countably finite or countable, bounded, 0 to 1, semi-bounded, 0 to infinity, unbounded, minus infinity to plus infinity. Okay. And chi-square is also very important. What happened is that some of this, remember the Bernoulli is, if I toss the coin 10 times, how many heads do I get? If I toss the coin 1 time, how many do I get? That has a special name, right? It's not called binomial. 1 is called Bernoulli. Okay, same thing like that. Gamma is a big family of distribution. If the first parameter is integer, it's called Erlang, or if the second parameter is 2, it's called chi-square or something like that. Now, the reason some of this would have a separate name is historical, because, you know, maybe you invent one first before you realize it's a special case of the other. Sometimes the name stuck because it's so useful. Chi-square is one of those. Okay, there's no reason why a gamma distribution with a second parameter of 2 should be that important. It turns out to be very important because it's chi-square. It's important, similar reason to that normal thing. Sometimes it's what's called derived distribution. Some kind of sampling technique would give rise to normal distribution if you sample all the time. If you sample in a different way, you get chi-square or something like that. So that's, you know, this is kind of like high tech now. This is where you need to talk to a statistician to choose. I mean, you can ask me, I can tell you that, but I won't have time to teach you that. But anyway, one of the most ubiquitous is this guy. Is this normal? This is how I create a function here. How do I create this kind of a thing? Technically, this is what it looks like, by the way, guys. This is the function. If you draw this function, it has this shape. Okay. So this is where, so if I did this, hold on, just click the whole thing, shift enter, just gonna make all kind of calculation. See, this is the shape, right? And yeah, so all this interactivity, all kind of stuff. So student T is like a multivariate. Now this is where you will play with only one, and that one's called bivariate normal. Okay, this one. So I'm gonna say, where's that example in class? Okay, plot. Okay, 3D in this case, PDF, binormal distribution. Okay, now I'm gonna make binomial distribution would have its own X and Y. Okay, and let's say X between -3 to 3 and Y -3 to 3. Okay, let's just do that. And so let's see. Okay, I'm just going to make life simple. I'm going to say the parameter. Binomial distribution again. Non-negative integer. Sorry, binomial. Binomial, not binomial. Okay. Okay. Right. What it means is that X is normal. X is normal. Y is normal. Right. And X and Y has a correlation. Oops. Has a correlation. So once again, let's do this. Manipulate. And then let's make this row. Row is escape, RHO, escape. Okay. You could just use R. That's okay. No big deal. Okay, there it is. Oh, chop heads off. So something when it's too long, automatically chops the head off. So I do this range plot range all, so it doesn't chop the head off. Okay, right. So let's start at 0. I'll give this to you so you can play. Now, what this means is that yes, X has its own distribution, Y has its own distribution, but the distribution of Y and distribution of X are not independent. So that if you knew, think about it, okay? Okay. Let me show you this. Where could X be? Where could X be? Anywhere, right? Anywhere, right? Where could Y be? Anywhere, right? Anywhere. But if I tell you what X is, okay, if I tell you what X is, say X is equal to 1 here. So I cut this line here. I still get that same shape, right? So that shape has to go up because it has to become something that integrates to 1. So that thing goes up again. Right now, the volume integrates to 1. But if you specify X, the curve of Y, this line here, has to go up a little bit so that the area underneath is 1. Make sense? Right? But when this line goes up, it looks the same. Okay? So it doesn't help. Right? X has normal distribution, Y has normal distribution. Knowing X doesn't help. However, if there's a positive correlation, knowing the value of X, shift your expectation of Y to the right. Right? Right? So this is multivariate distribution. Okay. How is this different from regression equation? With regression equation, you actually have Y as a function of X first, and then some noise around it. In this case, it's sort of like the distribution are tied together. So you can see that in this case, there's a positive correlation. So the higher X tend to be the higher Y. Okay. Where do you see something like this? A lot of time in the financial market, right? Return in one stock or one asset is random. So is the other one, but because it's the same market, whether or not you're talking about a corporate stock in Thailand or banking stock in Thailand, chances are they tend to move together. So that's a positive correlation, right? But there could be a negative correlation, like return from the bond market and equity market. Now, those are known in financial circle to be moving in the opposite way. When there's a boom in the bond market, there's a bust in the equity market. When there's a bust in a boom in equity market, there's a bust, boom and bust in the bond market. So this would be something like that. So this now, there are not that many multivariate distribution. And in fact, chances are you probably learn one, which is multivariate normal. Okay. If I had time, if last week's vote turned out to focus a lot more on statistics, I'll teach you more advanced probability, but I wouldn't. Okay. I'm just telling you this thing. Now, obviously, you can do X and Y. You can do X1, X2, X3. You can do X1, X2, X3, X4. So it has as many dimensions as you wish. Okay. However, you can't plot them. So that's it. Yeah, so that's multivariate. Let's go back to our sheet. Okay. Skip all this copula. That's the advanced stuff that I'm not teaching you. Now, let's go to estimation. Go to this page called estimated distribution. This one is also useful, but I don't use very much. Okay. Oh, sorry. I have to go back something. There's one more thing that I forgot to teach you. Okay. Once you have this binomial distribution, there's another function you should learn. Okay. It doesn't matter. Okay. It can be any kind of distribution. Okay. So what was it before? 0.3 and 10, right? Now, we did this, right? Mean of this, right? Now, let's play God. How do we play God? What if I were God? I would specify the distribution parameter 10 and 0.3. I don't give that solution to human. You know what I give them? I give them sample. So how do I give that? I give them what's called random variant. That's very important. Okay. So if I give them this, and I give 1,000 of them, 10 to the 1,004 something. Okay. So this is 10,000. Okay. Data equal to this. See that? It has all kinds of number. You can tell that it's between 0 and 10, right? Because you can only have 10 heads from 10 coin toss. Okay. Let's see. Let's see. Let's do this. COUNTS. Ah, see that? Now, this is not sorted. Okay. Now, you can sort from, never mind. Okay. So basically, out of 10,000, you can see a lot more in 2 and 4 and 3. 9, there's only 1 9. Look. That 10,000 cases, how many 9s do I have? There's only 1 9. Actually, there's no 10. Oh, there's 10. There is 10? No, there isn't 10. There's 0. Okay. Now, in other words, let's do histogram. See that? Now, histogram is going to look like a bar chart because it came from the data. See that? It starts from 0, no higher than 10. Actually, maybe there's a value here. That's basically looks like this. Right? It should look like this, right? Now, you can also do what's called smooth histogram sometimes. Sometimes it helps you to do smooth histogram. So a little bit like that. Okay. Now, technically, this is not good because binomial distribution is discrete. It's not continuous. So that smooth histogram is usually used for continuous. Okay. So there's that. There we go. Okay. Now, so I'm going to play both sides of the game. Okay. Okay. Here we go. Ready? Okay. Now, let's do this. So, as God, I would do this. I would generate data. Now, you saw this example already, right? So I'm going to make another example. Okay. Another example. Data 2. Okay. Now, you haven't close your eyes. You don't have to pretend. Okay. Pretend that you don't see this. Yeah. Yeah. Pretend that you don't see this. Okay. So let's okay. You don't see this. Okay. You don't see this. Now I go histogram. I see this. Okay. I see this. Better yet, I do smooth histogram. I see this. Okay. Now I also look at some data point. Data to say first 5, let's say first 10. It doesn't look like discrete number, right? So Poisson is not going to be that. But wait a minute, it's continuous, but it is non-negative, right? Right? How do I know that? Well, How do I do it? Min max. Oops. Okay. Min max of data 2. The minimum is 0.06. The maximum is 39. So nothing negative. That's a good hint, right? So I go to my trusty little diagram and say, you say that the distribution, probability distribution, right? Distribution, where is it? Probability distribution. If it's univariate, okay, univariate. Okay. Forget this one. I only do parametric. It's continuous, random variable, right? It's semi-bound. It's semi-bound. So it's either gamma or log normal. Okay. There's a special reason why this is a special case. But okay, gamma or log normal. Okay, gamma or log normal. Okay. Let's say I make a very good guess. Okay, I make a very good guess. So I'm going to say, I think it's a gamma distribution. Now, gamma distribution has two parameters. By convention, it's called alpha and beta. Don't worry, this is not important. You can just say B and A. Okay, alpha and beta. Okay. Now, if I chose this, this is one of my candidates. I'm going to do estimated distribution. Distribution, data 2, and this. I get this. Okay, see that? Again, this is one of those things that would take 25 lines to do in Python or R. Okay, just estimate the distribution of this data based on assumption that it's gamma. Okay, so I don't have to use that squiggly sign because it's a data. It's not okay. So that's what it would be. Okay, right. On the other hand, okay, let's say I make another guess. Let's make another guess. It's okay. Data, and I call this one is log normal. Okay, and it's called mu and sigma. Doesn't matter because it's just going to give the value anyway. Okay, so this is what I mean by statistical fitting. The best gamma fit is given by 2.04 and 2.91. The best by log normal distribution is this. Okay, they're not that different. It turns out. Well, actually, we can do this. Okay, we can say DIST1 equal to this, and DIST 2 equal, okay, right? How do I do this? I just plot them, right? Plot PDF of distribution 1, okay, of X. Now, what do I want to plot X from? X from 0 to unbounded, right? Infinity then. Okay. Now, obviously, Mathematica is not going to give you infinity. Okay. What happened is by default, it's just going to keep going until it gets close enough to 0. Okay. Filling axis. Okay. So that's distribution 1. If I want to plot distribution 1 and 2 together, right? I just put that in a set, right? Oops. Sorry. Wrong bracket. Okay. Okay, I want to plot PDF1 and PDF2. Right? So it's different, right? Different, actually, okay? Now, okay, because I am the creator of this data set, I know what I did, okay? I'll just show you here. It's gamma distribution with parameter 2 and 3, okay? So actually, when I estimate the data, I got 2.04 and 2.9. That's pretty close. That's pretty close, right? In fact, this one fits very good. So according to this distribution, according to my choice of distribution, let's say I choose this one. This one fits better than that. Now, how do I know this one fits better than that? Let's look at what we did. Find distribution. Let's try to something. Let's call this distribution 0 equal to find distribution it's going to take a while. It actually gets slightly different number, but it also agrees on gamma distribution. Okay. Sometimes it's numerically it's not stable, but it gets similar. So let's say this thing I find general search, yes, parametric estimation, that's the one with estimation parameter, right? Now, internally, it used this kind of method. Never mind. So you know how to do this. Okay. So let's say you didn't do this yourself, but your student did. Okay. You're not God, but you're the teacher. So you don't know the real underlying distribution, but one student did the homework. So I'm going to say one student. So this one I'm just going to take out for now. It's not, doesn't help much. Okay. One student came with this homework. The other student came with this homework. Who did a better job? Well, there's a way to find out. This thing is called distribution fit test. And that is here. Oops. Distribution goodness of fit. Okay. One of the thing in goodness of fit is distribution fit test. So say distribution fit test. Now, if you click F1, go to F1, what does it do? What does it expect? It expects data set, right? Okay, it's expect data set. So the data set is data 2. Okay. And the distribution you want to test, well, you have 2 students, right? Distribution 1, this is student 1. Okay. Now, I'm going to write something. You may not know what it means, but yeah, I write the word Kolmogorov-Smirnov. It is an invention by obviously two people, one named Kolmogorov, one named Smirnov. It's a technique for testing whether or not the claim distribution and the data fits well. Remember the hypothesis testing? I'm saying that some parameter is equal to 2.4. See if that's true. In this case, I'm not claiming against a number. I'm claiming against a distribution. My claim is data comes from distribution one, because that distribution one is a distribution fit that my first student did. One way of doing this is invented by the person named Kolmogorov-Smirnov, and it gives you a p-value. What this p-value says is that there's a probability of 0.53 that this data will come, this data or something, you know, along that line, fit this distribution. Okay, but it has a little bit of a, you know, great upper bound kind of thingy. Okay, whereas, okay, now let me show you. This is a second student. Well, before I go to the second student, let's do this. I know for sure. Let's give it another distribution that completely missed the boat. Really weird. Okay, let's say normal distribution. Okay. What's the p-value? 0. That means there's almost no chance that you can observe this kind of data coming from normal distribution. So obviously, if somebody fit, if one student came up with this, I would flunk him right away. Okay. But because this guy, this student came up with p-value pretty good. Remember p-value, you have some kind of cutoff like 0.01 or something like that. P-value of 50%, that's pretty impressive. So I'm willing to believe this student. Okay, so did he do his job well? Yes, he did his job well. But wait a minute, I have a second student who did better. Based on Kolmogorov, this guy didn't do very well. Okay. In fact, if I don't have this, let's say another student comes in and okay, also get gamma distribution, okay, but the parameter is way off. Now, you kind of know, you saw this before, it's 2 and 3, right? So let's make something really bad, say 1.5 and 1.5 and 3.5. See? So even if you get the right parameter, because you're so far away parametrically, right? You get 0 p-value. Okay. This is a warning of numerical. I can turn it off actually. Off. This is a warning for general number flow. Right. So let's say I put here 3. Yeah, so that's closer. Remember that that's still too far. So this really matters a lot. So how about 1.95? See that? Starting to get something positive, but still no good. So how about 0.197? Okay. So he gets positive, but you see how sensitive the test is? You have to be very good, and this is the one that's the best, right? And in fact, if you get the original, And here's something you might get confused. What about this? Okay, this is the true distribution. It gets higher, but it still doesn't get 1. Okay, because there's some randomness. But obviously, the estimate is very good. This estimate, bad, because I chose the wrong distribution family. But even if I chose the right distribution family, but the parameter is off, I still get 0 p-value. Okay. Time? Oh, geez, yes. Okay, sorry, guys. Okay, so thank you for the patience. I'll give you this, and you can do with it what you like. Again, go through. I encourage you to go through this. I'll give you the whole textbook, obviously, as not as a present, but as your learning material. But if you didn't go through this and understand the different steps, how I come up with the estimate, how I do the interactive visualization, and you understand the general concept, you'll be okay in midterm. Okay. Once again, the midterm will focus mostly on probability and statistics, simply because I don't really want to test you much on machine learning in midterm, because that's going to show up in your term project. Okay,ครับ. So next week we'll start with I think decision tree or something. Okay.